So welcome to this. This is the Further Maths Support Programme online revision session for MEI Statistics 2. And in this section we're going to be studying bivariate data. So bivariate data is basically where you're looking for relationships between two sets of data, bivariate data. So you need to know how to draw a scatter diagram, which I'm going to look at briefly. You also need to be able to calculate product-moment correlation coefficient, and also you need to be able to calculate Spearman's rank correlation coefficient. And you need to be able to perform hypothesis tests of these using tables of critical values. There are other ways, but they are out of syllabus, so we are expecting you to use critical values. Now the way you perform the tests is identical for each of these, but you still need to be able to know how to do them. So first of all, January 11, question 1. We've got a scatter diagram below. Now I'm not showing it just at the minute because we don't really need it straight away, but we've got what we call your summative data here. And say we'll look at the scatter graph when it becomes relevant in a minute. But here are your summary statistics, and we've got to calculate the PMCC, the product moment correlation coefficient. Okay, so there is a formula for this. It's R is equal to SXY over the square root of SXX SYY. So we need to work out each of these constituent parts. So let's do SXY first. So in your formula sheet we're told that SXY, which you could also do this using covariance and things, but this is the more standard way of doing it. But SXY is going to equal the sum of XY minus the sum of X, sum of Y over N. So this is going to give me 1398.56 minus 139.8 times by 140.4, all divided by 14. Okay, and you're going to get a method mark for this, which is quite nice. If we calculate that, that's going to give me minus 3.434. You then work out SXX. So SXX is the same, except it's sum of x squared minus the sum of x, all squared over n. So you're substituting your numbers in again. So 1411.66 minus 139.8 squared over 14. Okay, and that's going to give me a value of 15.657. You do the same for SYY. I'm not going to do that because it is identical. So SYY is going to give me 9869. So you're going to get yourself another method mark for calculating correctly either SXX or SYY, and you get an accuracy mark for all of them correct. Okay, whoops. And then we can then calculate R. So put in the numbers in the correct place, minus 3.434 divided by the square root of the product of those two things, so 15.657 times by 9.869, and that gets you an R value of minus 0.276. Okay, so you get a method mark here for using the formula and an accuracy mark for getting the correct answer at the end. So it's quite pleasant. As I say, you can do all of this using covariance and root mean squared deviations and things, but this is the more standard way of doing it, so that's what we expect. Okay, so we're then asked to carry out a hypothesis test at 5% to determine whether there is any correlation. So setting these out again, you get 3 marks for setting out a hypothesis test before we even start. So you get 1 mark for your null hypothesis, so it's the fact that rho, which is your population parameter for correlation, is 0, i.e. there is no correlation. It's not equal to 0 means that we have a correlation, and that's what we're looking for. And you need to tell me what rho is. So rho is the population correlation coefficient. So you get 3 marks just for writing that. Okay, B1, B1, B1. And it's 5%, and we're looking at 2-tailed here. Okay, so we need to use the correct tables for this. So let me show you how this works. For 5% 2-tailed, we're looking here. Our sample level is 14. We've got 14 pieces of data, and that leads me to this thing called your critical value. So here, your critical value is equal to 0.5324. And what we do is we look at the size of your test statistic. So your test statistic is the value that we created in the previous question. So the size of your test statistic is equal to 0.276. And as with the normal distribution, we're going to compare the size of the test statistic with the size of the critical value. And we can see that the size of the test statistic is smaller than the size of the critical value. So as before, we do not reject H0. Okay, so you've just picked yourself up 2 extra marks. Okay, a method mark for a comparison and an accuracy mark for getting this. Now, what we need to do is then contextualize. Okay, so there is insufficient evidence to suggest and again, correlation between birth rates and death rates. So you must put it into correct context when we do that. Okay, so for 6 marks, this is really nice. So here is the scatter graph that we had at the beginning. And it now says in part 3, state the distributional assumption which is necessary for the test to be valid. Explain briefly in the light of the scattergram why it appears to be valid. So what you need is you need both sets of data to be normally distributed. Okay, so we need bivariate normal. Okay, so we need each axis to be normally distributed. And what we're looking for that is what we call elliptic nature. So for it to be bivariably normally distributed, we're looking for what we call an elliptic nature. Okay, so that's what we need to state. So since the scatter graph is roughly elliptical, that's going to be sufficient in this case. Okay, don't forget a circle is an ellipse. It's just a special one, so that's quite important to bear in mind. Okay, so for instance, if your data formed a triangle, just because of how it works, then this wouldn't be true. So you get 2 marks. You get 1 mark for stating that it has to be bivariate normal, and you get an explainy mark for describing that we're dealing with elliptical nature here. Okay, the values of x and y for another country in the year are 14.4 and 7.8 respectively. If these values were included, the value of the PMCC is now minus 0.5694. Explain why this one observation causes such a large change to the value of the sample product moment correlation, and discuss whether this brings the validity of the test into question. Okay, now what we need to realize is this data point is miles away from everywhere else. If we look at the graph again, 14.4, 7.8 is going to be down here somewhere. Okay, so the data point is a long way from the other. Okay, it's below and to the right of. So that's really important. So it's extremal. Okay, and it's below and right. So making observations first of all. You've got 2 marks now, by the way, because you've just described what's going on. And it questions the validity. So validity is reduced since the point is extremal. Okay, because it's miles away, that's going to do that. So this is going to imply less evidence of ellipticity. I love that word. Okay, ellipticity. Because you can see, let me just go back to the graph, you can see that if you've got that extra point, it's just not really going to work very well. Okay, so looking at another question, June 10, question 1, we've got 2 celebrities and they're judging a talent contest. Each celebrity gives a score out of 20 to each of a random sample of 8 contestants, and the scores are given as shown below. And what we're asked to do in this case is to calculate the Spearman's rank correlation coefficient. So again, there is a formula for this, which we'll come to in a minute. As RS is equal to 1 minus 6 sum of d squared over n squared minus 1, where d is the difference in ranks, so we're looking for the sum of d squared. Okay, now it makes sense to try and order these because we need to rank them. It makes sense to try and order them in the way that is natural. So you would award first place to the person with the highest score. So when we start to rank this, we'll be ranking D as your first place for contestant X, and then B, and so on. Okay, please then also rank your other contestant in exactly the same way. It makes life a lot easier to do this. Okay, so there are my ranks, just to do this quite quickly, and D is the difference. Now I'm literally just going to subtract here, so we get 0, 0, 2, minus 3, minus 1, minus 4, 3, 3. Now you could argue that difference doesn't involve minus signs, but I think it's quite important here that we do consider them, because it's a check. If you add all of those D's together, you should get 0. Okay, and in this case we do, which is good. Okay, so we're then in a situation where we square these because we want the sum of D squared. So that's 0, 0, 4, 9, 1, 16, 9, 9. Okay, and if we add all of those together, we get a sum of D squared as being 48. Oops. So once we've got that, we can then use the formula. So we've now got 3 marks, by the way. We've got M1 for a ranking. Okay, so you get a method mark for an attempt at ranking. You get a method mark for attempting D squared, and then of course you're going to get your accuracy mark for getting that correct. So we've got everything we need now to work out RS. So RS is 1 minus 6 lots of 48 over n. Now n is how many pairs of data you've got, so that's 8 times by n squared minus 1, so that's 63. So working that through, we get 0.429. So you get an additional method and accuracy mark here. Okay, so moving on, we get a hypothesis test now, and again 6 marks, 3 for setting it up, 1 for your conclusion, and 2 for calculations. So this is exactly the same as we have for PMCC. So H0. Okay, now we have an issue here. Spearman's rank is a non-parametric test. We have no parameter to test against, so we need to use some words here. So we're asked to look at an association. So here we're going to say no association. Have to use words. So no association between the ranks of X and Y, and H1 will be an association. Now we don't really have too many issues with the use of dittos here, as long as you've defined it correctly. Okay, and we need the word population kicking around. Okay, so no association between the ranks of X and Y in the population. We need that statement. Okay, because that's really what we're looking for. So there are your 3 marks, 1 for each hypothesis and 1 for stating that you're dealing with a population. So as before, we need to find our critical values. So different table, we need to use the Spearman's rank table here, but it's exactly the same principle. So we're using a two-tailed test, and here we've got a level of 8. Okay, so we're looking in this particular case, association, so we're looking at a one-tailed test, 5%, get that correct in a minute. So we're looking at this particular value here. So your critical value is going to be 0.6429. We calculated your test statistic, which is your previous one. We calculated the test statistic to be 0.429. So again, we can see that the magnitude of your test statistic is less than the magnitude of the critical value, and that leads me to not reject H0 again. So not reject H0. So again, we've got 2 more marks here, and then your final mark is for your final statement. So the insufficient evidence to suggest a positive, that's why it's one-tailed by the way, positive association, to suggest a positive association between the scores allocated by the 2 celebrities. So again, it's putting it in full context here. Okay, that's very, very important. Okay, so it then says, state the distributional assumption for the test based on the PMCC and sketch a scatter graph. So we've seen this before, so the assumption is that we've got bivariate normal. Okay, and then you draw your scatter diagram. So here's my scatter diagram. And again, we're looking for elliptical nature. So you get, by the way, for your graph, you get 1 mark for your axes, Okay, and you get another mark for the points being correct. Okay, now notice it's the scores, not the ranks, it asks us to plot. And you can see here that we do not have an elliptical nature as such. Okay, so it says discuss whether it appears the assumption is likely to be valid. Here you can say lack of ellipticity. That's an explain mark, so assumption not valid for your second mark. Okay, so you can see the actual calculation of these and also the use in a hypothesis test is quite straightforward, but they are asking a lot about the distributional assumptions that you need. So you do need to make sure that you're fully aware of the bivariate nature that you are required to deal with, the ellipticity and bivariate nature.